Greetings of the day to all of you. In our previous lecture, last lecture, we discussed, in fact, we derived some very important mathematical expressions for active power transfer and reactive power transfer over an uncompensated power transmission line. Now the question is, why is there need for compensation? Why do we need compensation? Okay, so in today's topic of discussion is need for compensation. Why do we need to compensate a power transmission line? What is compensation? What are the functions performed by compensation? What are the types of compensators? That is the topic of discussion in today's lecture. So I will start with need for compensation. In order to understand need for compensation, let me take an uncompensated transmission line. I will write here uncompensated transmission line. Well, again, considering two machine model, in fact not a two machine model, let us consider a long transmission line and assume that power is transmitted or transferred over this power transmission line. The line reactance is X, Jx is the line reactance, and on the other side of line, suppose we have load. So this is an uncompensated system. Power is generated here, it's transmitted over long transmission line, okay, and this is the load. The power is consumed by the load here. The load voltage is, let us call it VR at an angle of 0 degree, okay. So this is the sending end voltage and this is the load voltage or voltage at the receiving end, the VR. Let us assume load impedance is Z and the load phase angle is theta. Impedance angle is theta. Load has an impedance Z at an angle of theta. Okay. Now if you draw the phasor diagram for this system, it's a very simple system. Let us take receiving end voltage as the reference. This is VR, receiving end voltage. I am taking it as a reference. Now assuming that load is reactive in nature, load is operating at lagging power factor, this may be the current flowing through the load, I, which is the same current which is flowing through the transmission network. Okay. Now resistive part of the transmission line impedance is neglected here. We are considering only the reactive part of the transmission line because transmission line reactance is predominantly very large as compared to resistance. So we can neglect the resistance of the transmission line. Now when this current which is drawn by the load, when it flows through the transmission line reactance, it causes a voltage drop across this transmission line reactance, which is Jix, and that drop will be at 90 degrees with respect to this current. If this is the current, this is Jix, then voltage drop Ji into X. You can see this current is at 90 degrees with respect to this. This drop is at 90 degrees with respect to this current. Okay. And then what is this? This will be the sending end voltage. Okay, the phase angle between sending end voltage and receiving end voltage is delta, which is also called power angle or transmission angle. And this transmission angle determines the flow of power over the transmission line, right? So this is the receiving end voltage, this is the sending end voltage. By simple Kirchhoff's voltage law, this sending end voltage is the receiving end voltage plus voltage drop across the transmission line reactance. Now as far as this current flowing in the transmission line is concerned, which is the current drawn by the load, we can resolve this current I into its resistive part and reactive part, or it has two components, in phase component and out of phase or quadrature component. Resolving this I into resistive part, which is in phase component of the current, plus reactive part, which is the out of phase or quadrature component of the current. The total current is IR plus IX, where IR is the in phase component of current, which is because of the load resistance, and Ix is the out of phase or quadrature component of current, which is because of the load reactance. Okay, so the phasor diagram then can be drawn like this. This will be our Phasor diagram. Again, this is my receiving end voltage which I am taking as a reference, and this is the current drawn by the load, which is the same current which flows through the transmission line I. Now I will resolve this current into two components. It will have in-phase component of current. Let us call that IR, where R stands for resistive component of current, and that resistive component of current is in phase with the voltage, and it determines the active power transfer to the load. Now this current will have a reactive component also, which will be quadrature at 90 degrees with respect to the voltage, and that will represent the reactive power. This IR represents the active power, and IX will represent reactive power. This is the reactive component of the current, or quadrature component of current, IX. Okay. Now, because of the resistive component of current or in phase component of current, and because of the quadrature or out of phase component of current or reactive component of current, there will be two types of voltage drops in this transmission line reactance. One voltage drop is JIX into X, which is the voltage drop because of law of quadrature component of current or reactive component of the current drawn by the load. Another voltage drop in this transmission line reactance is JIR into X, because when resistive or in phase component of current flows, that also causes a voltage drop. Now, as far as JIX into X voltage drop is concerned, it will lead the current, which is IX, by 90 degrees. That is the basic circuit theory. You know from basic circuit theory that in a purely inductive network, voltage leads the current, or in other words, current lags the voltage. Where is my out of phase or quadrature component of current or reactive component of current? IX. Now this IX will cause reactive voltage drop in the transmission line reactance, which is JIX into X, and that will be leading this current IX by 90 degrees. So that will be somewhere here. This will be from here to here. Let us call this voltage drop as delta V. And what is this delta V equal to? It is JIX into X. Now you can very clearly see, if this is your IX, and JIX into X will be at, this is delta V equal to JIX into X. Now you can see this voltage drop, JIX into X, it leads the current by 90 degrees. Or in other words, the current lags the voltage by 90 degrees, which is the fundamental principle of a reactive circuit. So therefore, because of this reactive component of current, it causes a voltage drop across this line reactance, which is given by delta V equal to JIX into X, which is at 90 degrees, which is leading by 90 degrees with respect to this IX. Okay, now there is another drop in this transmission line reactance, which is because of the resistive component of the current or in phase component of current, IR. Where is IR? IR is here. See, for example, if this is your IR, where will be the resistive voltage drop? Resistive voltage drop will be JIR into X. I mean reactive drop across the transmission line, which is because of resistive component of current, JIR into X. This voltage drop will also lead the current by 90 degrees. What is the current which causes this voltage drop? It is IR. And this IR causes voltage drop across this transmission line reactance, which is given by JIR into X. So it is at 90 degrees with respect to IR. And therefore, where is your IR? This is IR. So if this is IR, then this will be JIR into X. This will be reactive voltage drop due to the in phase component of current. Delta V equal to JIX into X is the reactive drop, is the voltage drop across the transmission line reactance because of out of phase component of current or quadrature component of current, and JIR into X is the reactive voltage drop across this transmission line reactance, which is because of the in phase component of current IR. Okay, so therefore, what is this? This is JI into X. It is just like this in the previous Phasor diagram, where we had not resolved I into in phase and quadrature components, where we had taken I itself. The reactive voltage drop was JIX. Here also you will get same reactive voltage drop, JIX, which is equal to JIX into X plus JIR into X. Okay, so therefore this will be your sending end voltage Vs. And the angle between sending end voltage Vs and receiving end voltage Vr is delta, which is again power angle or transmission angle. Now therefore, if you take I only into consideration, this is Vr, this is Jix, and this is Vs. So it is same as this phasor diagram. But if you resolve this I into in phase component IR and out of phase or quadrature component Ix, then you can show both the voltage drops. Voltage drop because of out of phase component, which is given by delta V equal to Jix into X in this direction, and voltage drop because of in phase component of a current, which is JIR into X. And this is your total voltage drop, Ji into X, and this is Vs. Now again you can see Vr is less than Vs, or in other words, Vs is greater than Vr. So that means receiving end voltage is less than sending end voltage by what amount? By the amount of the voltage drop. Now as far as the voltage drops are concerned, you can see there are two voltage drops. One is because of reactive component of current, which is given by Jix into X. Delta V equal to Jix into X is mainly responsible for voltage drop across transmission line reactance, because you can see it is your sending end voltage is receiving end voltage, your receiving end voltage is sending end voltage minus this, directly subtracts from here. And as far as voltage drop JIR into X is concerned, which is the voltage drop across the transmission line reactance because of resistive or in phase component of current, it does not it does not matter much. Voltage drop due to resistive component of current, which is JIR into X, is very, very small. Okay, it is small. It is negligibly small. So what is the main voltage drop which causes receiving end voltage to be less than sending end voltage? This delta V, as Jix into X, which is because of the quadrature component of current, and this quadrature component of current represents the reactive power. Resistive component of current or in phase component of current IR represents the active power. So therefore the voltage drop because of active power, which is JIR into X, it does not significantly change it does not significantly result in the drop of the voltage. But the voltage drop because of the reactive component of current, which is because of the reactive power flow, reactive power drawn by the load, it is mainly responsible for drop in the voltage. So your receiving end voltage is sending end voltage minus this drop. Okay, so therefore that's why you must have studied in your power systems course also that it is the reactive power which is mainly responsible for poor voltage regulation in a power system, which is mainly responsible for voltage drop across the transmission line reactance, and that is proved by this phasor diagram also. Delta V equal to Jix into X is main drop which makes your receiving end voltage less than sending end voltage, or which makes sending end voltage more than receiving end voltage, and hence results in poor voltage regulation. Larger the reactive power drawn by the load, larger will be the magnitude of Ix, that is quadrature component of current. So larger the Q, larger will be the Ix, and larger will be delta V, and larger the delta V, smaller will be the receiving end voltage. Okay, so and poorer will be the voltage regulation. So therefore one of the main drawbacks of uncompensated transmission line is that if the load draws a significant amount of reactive power, that load reactive power will be mainly responsible for drop in the voltage through the line reactance, and that will cause receiving end voltage to be less than sending end voltage. And if the reactive power drawn by the load is very large, then this drop will be very large and receiving end voltage may become much smaller than sending end voltage, and it will result in poor voltage regulation at a particular bus. Voltage regulation will be poor. So therefore uncompensated transmission line is a problem. We cannot just go for uncompensated transmission line, because if a substantial amount of reactive power is flowing over the transmission line, that will cause delta V to increase, and that will cause VR to be much less than Vs, and that will cause poor voltage regulation. So therefore there is a need for compensation. I will draw this diagram again here. This is VR, this is current I, theta, This is in phase or resistive component of current IR. This is reactive or quadrature component of current IX. This is delta V equal to JIX, reactive voltage drop, JIX into X, and this drop is JIR into X, voltage drop due to this in phase component of current. This is JI into X, and then this is sending end voltage Vs. You can see receiving end voltage is less than sending end voltage, and hence poor voltage regulation may result in an uncompensated transmission system. Your load voltage may be much less than the rated voltage if large reactive power is flowing over the line, because large reactive power flow means large reactive component of current Ix, and that means larger drop delta V. Therefore, there is a need for compensation. Now, how to make compensation? There are two methods of compensation. So therefore, there is need for compensation. One of the reasons for compensating an uncompensated transmission line is to improve the voltage regulation, which we have just now seen that this voltage regulation may become very poor depending upon the reactive component of current or reactive power drawn by the load. So therefore, now we wish to improve the voltage regulation. We wish to compensate the transmission. Now there are two ways by means of which we can do the compensation. One is called load compensation. One method is called load compensation, where you will compensate load reactive power itself. You will connect a compensator across the load itself. You will not connect compensator along transmission line, but you will connect compensator across the load itself, just like we are connecting a D-STATCOM or a capacitor bank across the load, which we have studied in power quality problems and solutions course. You may have to connect a custom power device across the load, which will custom power device, best example is D-STATCOM, which will fulfill the reactive power demand of the load, and hence it will improve the voltage regulation. Let us see how it does. But before we go for that, another method of compensation is system compensation. System compensation. Load compensation means that you are compensating the load itself. That will automatically cause transmission line this compensation. Another method of compensation is system compensation. In system compensation, you connect a series FACTS controller or a shunt compensator, either a series compensator or a shunt compensator across the transmission line, maybe in the middle of the transmission line or anywhere along the length of the transmission line, for compensating the transmission line. Okay, that is what is done in FACTS. In FACTS, we go for system compensation. We don't go for load compensation. Okay. Now let me show you how load compensation results in improvement in the situation. So we will go for load compensation. So this is the power circuit diagram for load compensation. This is sending end voltage Vs at an angle of delta. This is transmission line reactance Jx, and the current flowing is I. And this is the load, which is drawing current I, or which requires certain power. Load impedance is Z at an angle of theta, and receiving end voltage here is VR at an angle of 0 degree. Okay. Now what we are doing, we are connecting. I should write it here. Receiving end voltage VR at an angle of 0 degree. What we do in load compensation, we compensate the load itself. We connect a shunt compensator across the load. Here I am showing a simple capacitance or capacitor bank connected across the load. It could be an active compensator also. Active compensator means D-STATCOM. If you are connecting only capacitor bank across the load, it's called passive compensation. But if you want to do active compensation, then this capacitor will be replaced by D-STATCOM. You are connecting D-STATCOM across the load. Anyway, whether it is passive compensator or active compensator, we will show this compensator by this diagram. A capacitive compensation is done. Okay, and because of this, a capacitive current IC is flowing and load current is, for example, IL. Let's assume load current is IL. Let me tell you how this load compensation improves the voltage regulation of the system. For that purpose, we will reproduce the phasor diagram again. Again, this is my receiving end voltage VR, and this is the current which is flowing over the transmission line because of the load connected and theta. Now again I will resolve this current, transmission line current, into in phase component IR and out of phase or quadrature component IX. Now we already know because of this IX there will be voltage drop across this transmission line, reactance JIX into X, which will be at 90 degrees with respect to IX. If this is IX, that drop will be JIX into X. Let's call that drop as delta V1, and that delta V1 will be like this. This is यहाँ से यहाँ तक, this is the voltage drop, delta V1 equal to JIX into X. It is the voltage drop across the line reactance, and it is at 90 degrees with respect to the current IX. It's leading current by 90 degrees, or this current IX is lagging this voltage drop delta V1, which is equal to JIX into X by 90 degrees. Now in this case, what we are doing, we have connected a capacitor also. By proper designing of the compensation technique, this capacitor will inject a current IC, which will be equal and opposite to the reactive component of load current IX. IX is the reactive component of current drawn by the load. When I am connecting capacitor across the load, the capacitor injects a current IC, which is equal and opposite to IX, and hence it cancels the effect of IX. Okay, now when this capacitive component, assume that this capacitive component of current flows through the transmission line reactance also. When it flows through transmission line reactance, it will result in voltage drop across this transmission line reactance, which is minus JIC into X. See, voltage drop delta V1, which is because of reactive component of the current, is JIX into X, which I have shown here. Now because now as you have connected capacitor also across the load, there will be capacitive component of current also, and that capacitive current component of current will be, let me call that delta V2, that will be equal to minus JIC and X, IC into X, that will be equal and opposite to delta V1. So where will be that delta V2? That will be like here. This is delta V2 equal to minus JIC into X. Again, you can see if this is a capacitive current, this is the voltage drop due to capacitive current. And this voltage drop is leading the current by 90 degrees, or this IC is lagging delta V2 by 90 degrees. Okay. Right. Now, this delta V2 will be equal and opposite to delta V1, because delta V1 is because of reactive component of current, and it is equal to JIX into X. When you are compensating the load, the compensator injects a capacitive current IC, which is equal and opposite to IX, and it causes another voltage drop delta V2, which is equal to minus JICX, which is equal and opposite to delta V1. So therefore, if this is delta V1, this will be delta V2. This will be, I will write here, delta V2, which is equal to minus, or I will write it here itself, delta V2 equal to minus JIC into X. Delta V1 is because it is equal to JIX into X. It is positive voltage drop, and delta V2 is because of the compensator injected current IC, and it is equal to minus JIC into X. It is equal and opposite to the delta V1. So delta V2 is equal to minus delta V1, and you can see this delta V2 is equal and opposite to delta V1. It compensates, it cancels out this voltage drop due to IX component. So therefore this is delta V1 and this is delta V2, and delta V2 is equal and opposite to delta V1. So this drop is gone. There is no reactive voltage drop because of the reactive component of current, because of the load compensation. But there will be a resistive component of current also drawn by the load, and that resistive component of current will also flow through transmission line reactance, and that will cause, which I have shown here also, JIR into X voltage drop. It will cause JIR into X voltage drop, and therefore your sending end voltage will be this. This is sending end voltage Vs. The angle between Vs and Vr is delta, which is also called power angle or transmission angle. Now you can see in this case that Vr is very, very nearly equal to Vs, because the reactive voltage drop because of in phase component of current, that is JIR into X, it does not make much difference. This drop is negligibly small, so that receiving end voltage in this case is nearly equal to sending end voltage, and voltage regulation will be nearly equal to 0. That means your whatever was the voltage drop delta V because of the flow of reactive power, because of reactive component of current, that is being compensated by capacitor voltage drop, which is delta V2 equal to minus JIC into X. So delta V2 compensates or cancels delta V1, and then you have only resistive voltage drop due to resistive component of current, and this is Vs. So in this case, what you are doing by providing the load compensation, you are eliminating this voltage drop delta V1, which was very much present here, and it was this voltage drop which was mainly responsible for making VR less than Vs. And now you have only this JIR into X, that is reactive voltage drop due to the in-phase component of current, which is significantly small because it's not directly subtracting or adding to this. It is at 90 degrees. So this is your Vs. So Vs is very nearly equal to Vr, or Vr is very nearly equal to Vs. So that improves the voltage regulation of transmission line. So this shows why we need compensation. In order to improve the voltage across the load, that is in order to improve the voltage regulation, a shunt compensator I have connected across the load. This is called load compensation, and this shunt compensation or load compensation results in Vr very nearly equal to Vs. I hope this is clear to you. So therefore, there is a need for compensation. When we do compensation, the first advantage that we are achieving is that load voltage profile improves. The load voltage improves because this drop, because of the reactive component of current, is compensated by capacitive current. Whatever is the reactive power demand of the load physically, that is being supplied by this shunt compensator, it does not have to come from the source, and that decreases the voltage drop across this line reactance and improves the receiving end voltage. Your receiving end voltage very nearly becomes equal to sending end voltage, which we have just few moments back seen through the Phasor diagram. So therefore, this is what is the advantage of load compensation. Another type of compensation I have already told you is called system compensation. And I have already told you in system compensation, we are not compensating the load, we are compensating the transmission system. You may connect a shunt or series capacitor in series with the transmission line, or a shunt capacitor across the transmission line for system compensation. And that will also improve the voltage regulation of the system, and that will also result in other advantages. So therefore, what are the functions of compensation? If you write, we can write the functions of compensation. What are the main functions of compensation, whether it is load compensation or system compensation? We need compensation of an uncompensated transmission line because of following reasons. We will understand it with the help of, after we have, I will now write main functions of compensation. The first main function of compensation is, I will write here, I will note here, to maintain substantially flat voltage profile, at different transmission levels, That means it results in better voltage regulation, better VR. VR means voltage regulation. Just few moments back, we have proved through the Phasor diagram that the compensation improves the voltage profile of the system. If your voltage profile without compensation is like this, it improves the voltage profile of the system. It makes it constant like this. There may be some small drop. Your VR may be very nearly equal to Vs. This is Vs, this is VR. So therefore, this is what compensation does. The first main function is that it improves the voltage profile at different levels of transmission. That means it results in better voltage regulation. Okay, so consumer load will get a good voltage. There will not be much drop in the voltage if compensation is done. So it will result in better voltage regulation. Second function of compensation is to reduce the power loss and hence increase the efficiency of transmission, and hence increase the efficiency of transmission. It is very much clear, because see, without compensation, there are two components of power which are drawn by the load: active component, active power, and reactive power. Higher is the reactive power, more will be reactive power drop, and more will be the active power drop. I square R, it will increase more and more. Now this I has two components, in phase component, and it has out of phase or quadrature component, which is also called reactive component of current. And this Ix is because of the load reactive power. Larger the reactive power of the load, larger will be the magnitude of Ix, and larger Ix, larger will be I, and more will be the I square or losses in the transmission line, and more the power loss in the transmission line, poorer will be the efficiency of transmission. Now when you are doing the compensation, in case of compensation, the reactive power is supplied by the compensator itself. It does not have to come all along from the generating station. No reactive power will be supplied by grid or by generating station. Whatever is the reactive power demand of the load, that is fulfilled, that is supplied by the compensator itself. So what that does, that reduces the reactive component of power which is coming from the source, which is coming from the generator, because this reactive power is supplied not by the generator, it is mostly supplied by the compensator. And since Q is now reducing, Ix is reducing, and when Ix reduces, power losses, that's I square R loss, will decrease, and efficiency of transmission will also improve. So it will increase the efficiency of power transmission. Third function is to improve the stability of the system. To improve the stability of system. We will study in future lectures that how compensation, whether it is shunt compensation or series compensation, how it improves the transient stability of the system. Whenever you are connecting a compensator across a transmission line or in series with a transmission line, that compensator improves the stability of the system. Next is to increase the power transfer capability, of an existing transmission system, That means to improve the utilization of equipment. Let us consider an uncompensated transmission system. In an uncompensated transmission system, the load reactive power demand may be high, and since this reactive power has to come from the generating station, so the line may be carrying substantially large reactive power, and it will not be able to transfer the required amount of active power, because reactive power component is very large. Okay, so for the given volt ampere or kVA or MVA rating of the transmission line, if the reactive power in an uncompensated system is large, then active power transfer will be less. What compensator does, it decreases the reactive power drawn by the system from the generating station. The less reactive power is coming from the generating station, and the reactive power demand is fulfilled by the compensator. So that way the more active power can be made to flow on the existing transmission line. So therefore that means it improves the utilization of the equipment. The generator, transformer, transmission lines, they carry more active power. Their active power transfer capability of transmission system improves. So this is another advantage of compensation, or another function of compensation. Fifth and last function is to damp the electromechanical oscillations, or they are also called power oscillations, quickly. A small disturbance in the system will render your uncompensated transmission system unstable, and there may be huge electromechanical oscillations or power oscillations. But when you are connecting a compensator across a transmission line, you are compensating your transmission line. Your transmission system is not uncompensated, it is compensated. So the compensator, whenever there is a disturbance, the compensator immediately damps out electromechanical oscillations or power oscillations and makes the system more stable. So we will study this damping of power oscillations by various types of compensators in future classes. So therefore we have discussed main functions of the compensation. First is to improve the voltage regulation, to maintain substantially flat voltage profile at different levels of transmission, which just few moments back we have understood with the help of Phasor diagram. For a compensated transmission system, the receiving end voltage increases, it improves, and in the extreme case it may become same as sending end voltage. So voltage profile improves. And then to reduce power loss and increase the transmission of efficiency, to increase the efficiency of transmission. When you are compensating an uncompensated transmission line through a compensator, so reactive component of current carried by the transmission line Ix decreases, so that decreases I square R loss, and that therefore increases the this efficiency of transmission. Third function of compensation is to improve the stability of the system. In presence of compensators or for a compensated transmission line, the stability margin is higher. Then next was to increase the power transfer capability of an existing transmission system. Using a compensator, it may be series compensator or shunt compensator or a combination of these compensators, an existing power transmission network can be made to transfer more power, more active power. So therefore power transferring capability of an existing transmission system can be improved. And finally, whenever there are oscillations, power oscillations due to some disturbance, the compensator very quickly suppresses or damps out the oscillations. So these are the main functions of compensation. So how do we define then compensation? Let us define compensation. Definition. I will give you the definition of compensation. I will write here, compensation is defined as a modification in the electrical characteristics of a transmission line, in the electrical characteristics of a transmission line, for increasing its power transfer capability, for increasing the power transfer capability of the line, power transfer capability of transmission line while satisfying the fundamental requirements of transmission, power transmission, while satisfying the fundamental requirements of power transmission that of stability and acceptable voltage profile. These are the fundamental requirements. And acceptable voltage profile. See, this is a very concise and very interesting definition of compensation. I will read it again. Compensation is defined as a modification in the electrical characteristics of a transmission line for increasing the power transfer capability of transmission line while satisfying the fundamental requirements of power transmission, that of stability and acceptable voltage profile. I have a transmission network. I want to improve its power transfer capability, so I am using compensators. So what these compensators actually do, they modify the electrical characteristics of the existing transmission network so that the same transmission network transfers more active power. Its power transfer capability increases. However, when you do this, when you compensate a line to improve its power transfer capability, fundamental requirements of power transmission have to be satisfied. And what are those fundamental requirements of power transmission? Stability and acceptable voltage profile. It should not be that you are making a particular transmission line to carry more power, but the line becomes unstable and its voltage profile deteriorates. No. If that happens, then your compensation has some fault. This is not a proper compensation. A good compensation, good level of compensation is that in which the power transfer capability of the existing transmission line improves while satisfying the main requirements of power transmission, that is stability and acceptable voltage profile. The transmission system becomes more stable, and also voltage profile is acceptable. There is not much drop in the voltage, rather the voltage profile improves. So this is the definition of compensation. So compensation basically means modification in electrical characteristics of a transmission line. We'll study that in next class. We'll use a shunt compensator, a series compensator, and a phase angle compensator, and we'll see how it modifies the electrical characteristics of a transmission system so that this transmission system can carry more power while maintaining or satisfying stability and acceptable voltage profile. So that is definition of compensation. Now, what are the types of compensation? Types of compensation. There are mainly three types of compensation. One is line length compensation, line length or series compensation. In series compensation or line length compensation, we are connecting generally a variable capacitor in series with the line. When we connect a variable capacitor in series with the line, that effectively reduces the line length. I mean, length of the line we are not decreasing. If the line is 700 kilometer long, it will remain 700 kilometer long. But series compensation will make this length of the line look like small. It may effectively decrease the length of the line. It will be still 700 kilometer long transmission line, but it will have the effect of smaller length of the line. And small length of the line means more power transfer capability, more stability, and damping of power oscillations effectively. Okay, so in series compensation, generally an inductor or a capacitor, variable capacitor is connected in series with the line, and it improves the stability of the line. It makes the line to carry more power and all that. This is called line length compensation or series compensation. Second is compensation by sectioning. Compensation by sectioning a line, or this is also called shunt compensation. Shunt compensation. So what we are doing in this case, we have a compensator. It's not connected in series, it's connected across the transmission line. In shunt means parallel or across. And then a transmission line is sectioned into small sections. We will see that in next lecture, that when a shunt compensator is connected, say for example in the middle of a transmission line, it divides transmission line into two sections, one on this side, another on other side. And if you have more than one shunt compensators, then you will have more sectioning, more sections of a transmission line. Okay, so by doing that, by sectioning of the transmission line using shunt compensators, we can also do a very good or effective compensation. How that is done, we'll study in next class. Third is phase shift or phase angle regulation. Phase shift or phase angle regulation. Phase angle regulation, which is also called PAR. P for phase, A for angle, and R for regulator or regulation. So we have certain FACTS devices which are called phase angle regulators. With the help of those FACTS devices like phase angle regulator, we change the phase angle of the transmission network, and hence we can make it to transfer more amount of active power. Its power transfer capability can be improved, and it can be made more stable. Its voltage profile can also be improved. So therefore, these are three main types of compensations. We have to study these three types of compensation in details in future lectures. We have shunt compensation, which is also called compensation by sectioning. We have series compensation, which is also called line length compensation, and we have phase shift or phase angle regulation type compensation. We'll study these types of compensations one by one in future class. Now, this was types of compensations. Now, what will be the types of compensators? Compensation will be actually provided by physical devices, which are called compensators. What are the various types of compensators? Actually, we may have two main categories of compensators: passive compensators and active compensators. I will write here A, passive compensators, and B will be active compensators. Active compensators. When I say passive compensators, it means series capacitance or shunt inductance. We may have to connect a inductance across a transmission line, or we may connect a series capacitance in series with the transmission line. Okay, C we connect in series with the line, and L we connect across the line. So these are passive components. Capacitor and inductors, they are passive components. That's why this type of compensation is called passive compensation, or this type of compensators which connect C in series or L in parallel with the transmitter, they are called passive compensators. Okay, so these passive compensators are permanently connected, or they may be switched. Switch means whenever you need a compensator to be connected, you can switch it on. You can put it in series. For example, if it is a capacitance, you can put it across the this transmission line, or in series with the transmission line, or you can put L across the transmission line. That's called switching. Or sometimes they are permanently connected as compensators. We don't switch them, we permanently connect them. Then third feature is no continuous variation. No continuous variation. I mean, if you have a C or an L, these C's or L's, they are connected in series or across transmission line, they do not result in smooth and continuous variation of capacitance or inductance. The capacitance or inductances may be added in steps, so continuous variation is not possible with the help of these passive compensators. And let me tell you that these passive compensators are very, very larger in size. They are bulky, and their cost is high. They occupy a lot of space, and they have some other technical problems like resonance problem and all that. So that's why passive compensators are generally nowadays not used for compensation of transmission lines. Passive compensators were used earlier in earlier grid stations or earlier transmission networks. But in modern power transmission networks, we don't use passive compensators, we use active compensators. Active compensators actually comprise of thyristor controlled compensators or converter based compensators. There also we use C's and L's, but those C and L, they are made variable C or variable L with the help of converters or with the help of thyristors. Okay. So active compensators, their main job is to maintain substantially constant voltage. Substantially constant voltage. Whenever an active compensator is connected across a line or in series with a line, first job it does, it improves the voltage regulation of the system. It improves the voltage profile and hence tries to make the bus voltage constant. That's number one. Number two is that these active compensators generate or absorb precise amount of reactive power. Precise amount of reactive power in response to a variation or in response to variations in the voltage at their point of connection. at their point of connection. For example, you may have a shunt compensator connected across a transmission line. Whenever the load voltage, this transmission bus voltage varies, the reactive power may be either injected by your shunt compensator or it may be absorbed by your shunt compensator depending upon the need, and hence it tries to either generate or absorb precise amount of reactive power in response to even small variations in the voltage at the point of connection, and hence maintain the bus voltage constant. Okay, and third feature is that continuous variation is possible with the help of active compensators. Continuous variation, they result in continuous variation and their response is fast response. On the other hand, if you have passive compensators, when you want to switch in or switch out a passive compensator, we are switching in or switching out them mechanically using mechanical switches, so their response is slow. But if you use active compensators are electronically controlled, they don't use mechanical switches, and they can very quickly get connected to the system and make the reactive power compensation, generate or absorb precise amount of reactive power, and the variation of the reactive power generated or reactive power absorbed is continuous, whereas there is no continuous variation possible in passive compensators. So this is a brief comparison between passive compensators and active compensators. So because of these features of active compensators, in our lectures we will mostly discuss active compensators like active series compensators, active shunt compensators, active series compensators, and active series shunt compensators, and phase angle regulators and voltage regulators. We will discuss only active compensators. So this is about the types of compensators. So therefore, let me stop my lecture today. In this lecture, we have tried to underscore the need for compensation. The question is, why do we need transmission line compensation? I have tried to explain that with the help of phasor diagrams. First of all, we drew the phasor diagram of a transmission system, of a system without compensation, and we saw that the reactive power drawn by the load is mainly responsible for reactive voltage drop, JIX into X, across the transmission line reactance, and hence poor voltage regulation. It makes receiving end voltage less than sending end voltage. Okay, and then we found that there is a need for compensation, and if you do the compensation, for example load compensation or system compensation, the reactive voltage drop because of the reactive component of the current, that gets nullified by capacitive reactive voltage drop, because if you are connecting a capacitor across the load, the capacitive current will cause a voltage drop which is equal and opposite to the inductive voltage drop, and hence they cancel out each other, and the only drop in the system remains then reactive voltage drop due to the in phase or resistive component of current, which is not much, which is not significant, and hence it improves the voltage profile or voltage regulation of the transmission system, making the receiving end voltage very nearly equal to sending end voltage. We have tried to understand it with the help of phasor diagrams, and then I summarized the main functions of compensation. Why do we go for compensation? For example, for improving the voltage profile, making it almost flat, for improving the stability of the system, for damping out the oscillations, for reducing the power losses and increasing the efficiency of transmission, and for increasing the power transfer capability of an existing transmission line. These are the main functions of compensation. And then I defined the compensation. Definition of compensation also I have discussed with you. And finally, we discussed types of compensation like series or line length compensation, the sectioning compensation by sectioning of the line or shunt compensation, and phase angle regulation. And then finally we discussed the types of compensators. Compensators are mainly of two types, either passive compensators or active compensators. Because of these features of active compensators, in modern day transmission systems, we are mainly using these active compensators, and these active compensators are nothing but facts devices. So hopefully, inshallah, in our next lecture, I will discuss the active compensation, or I will discuss the compensation, shunt compensation, series compensation, phase angle regulation in details with you. We will first of all take ideal shunt compensation, and we will see how this ideal shunt compensation compensates an uncompensated transmission system for better voltage regulation, increased efficiency of transmission, better transient stability, and all that. We'll first discuss ideal shunt compensation, followed by ideal series compensation, and phase angle regulation compensation. So with this, I will end my today's lecture. I advise all of you to go through this lecture and put your queries, if any, on the group. All the best to all of you. Thank you.